Okay, in this video, we will explain the notion of Laplace transform and some of the basic properties. Let me start by saying that the Laplace transform is somehow similar to the derivative. For example, the derivative takes a function, f of t, let's say the function t squared, and it produces another function, the function f prime of t equal to t. The Laplace transform will take a function, let's say it takes the function f of t equal t, and it will produce another function. But one of the differences is that the independent variable of the initial function, which is t, is different from the independent variable of the Laplace transform. The Laplace transform of this function is this function, f of s equal 1 over s squared. We can do the graph, the Laplace transform. Usually we consider only when t is bigger than 0. This function has a graph like this. And this function, this is f of t equal t, and this is t. And here we have s, and the other graph is like something like this. This is f of s equal 1 over s. Then the Laplace transform takes a function into another function, but one of the differences is that the independent variable of the input function is t, and the independent variable of the output function is s. Let's see what is the definition of Laplace transform. Maybe before that, we should point out that if we have an integral like the integral from 1 to t dt, this is a number. This is just the antiderivative of t is t squared over 2. When you evaluate from 0 to 1, you get 1/2. But if you have an antiderivative, let's say from 1 to 2, from 0 to 1, of the function, let's say sine of k times t dt, sorry, let's not call it this, sine of s times t dt, then when we integrate with respect to t, everything is gone, but the s stays there. How do we do this integral? We can do a substitution, u equal st, then du is equal to s dt. That means that this integral, to do this antiderivative, sine of st dt, it becomes the antiderivative of sine of u, and the dt is 1 over s du, and that means that this antiderivative and the antiderivative of sine is negative cosine of u over s. That means that this is negative cosine of st over s. We replace u by st. That means that this antiderivative is just the antiderivative negative cosine of st over s, evaluated from 0 to 1. And when we evaluate at 1, t equal 1, we get negative cosine of s. And when we evaluate at 0, cosine of 0 is 1, then it's just negative 1 over s. That means that this is negative cosine of s plus 1 over s. Then the whole point with this is that when we have an integral and there are some bounds, some limits, and we are integrating with respect to t, it's like the t disappears and we are left with some function in terms of s. This is what is going to happen with the Laplace transform. Okay, after doing this example, let's try to see the definition of Laplace transform. For the Laplace transform of a function, f of t, this is Laplace transform, and here the input is the function f of t, we get is equal to this, the integral from 0 to infinity of f of t times e to the negative st dt. Notice that this integral, there is a t there, but there is an s. And when we integrate with respect to t, the t is going to disappear, and we're going to be left with a function in terms of s. That's the reason we start with a function in terms of t, and we end up with a function in terms of s. Another observation is that this is an improper integral because we have an infinity here. Let's do our first example. Let's suppose that we want to do the Laplace transform of the function 3. Notice that we are going to start with this function. This is t, and the function 1, 2, 3. This is this function, this constant function. This is f of t. Then, according to the definition, we have to do an integral. It's the integral from 0 to infinity of the function f of t, which is 3, times e to the negative st dt. But when we do a substitution, then we know that the antiderivative of this is going to be negative 3 over s e to the negative st. Notice that when we do the derivative of this with respect to t, there is a negative s that comes down, and it cancels this negative s, and we end up with this. This is an antiderivative, and when we evaluate from t equals 0 to t equals infinity, usually here, if s is bigger than 0, we have that when we evaluate, when t is big, we have like e to the a negative number, and e to the negative number is 0. And then we have 0 minus, and when we evaluate at t equals 0, then we have negative 3 over s e to the 0. That means that this integral is just 3 over s. And this is the antiderivative, this is the Laplace transform. Then we have shown that the Laplace transform of the function 3 is the function 3 over s. And something that we're not going to be worried about is the domain of the Laplace transform. Notice that the domain of the Laplace transform is s bigger than 0. Usually the domain of the Laplace transform is going to be s bigger than a positive number, or bigger than a number, but we're not going to care much about the domain of the Laplace transform. We're going to only care about this, that it takes this function into this function. And in the same way, what happens if we replace 3 by a, like any number, 7, 17, pi, then the computation shows that the Laplace transform of a is going to be a over s. For the definition of derivative, we have that the derivative comes with a limit, but when you do a derivative, you usually don't do that limit. You just remember the properties. You just remember that the derivative of t squared is 2t, the derivative of sine of t is cosine of t. It's going to happen the same for the Laplace transform. You don't have to do this integral to compute the Laplace transform. Actually, I may be asking that in a test, but usually to do the problems, you don't have to do this. You just need to remember these values, this table, and actually I'll be providing a table. Okay, let's do another example. What happened if we want to compute the Laplace transform of the function e to the 2t? Then, according to the definition, this is the integral from 0 to infinity. Instead of f of t, I have to write e to the 2t, and then here e to the negative st dt. And this is just the antiderivative from 0 to infinity of e to the, using the properties of the exponential function, this is 2 minus s times t dt. And if I do a substitution, then this would be 1 over 2 minus s e to the 2 minus s times t. Notice that the derivative of this function, when you do the derivative, this 2 minus s comes in front and it cancels that, and we end up with this. And we're going to evaluate this from t equals 0 to t equal infinity. Notice that if s is bigger than 2, then this quantity, when t is big, it goes to 0. Then we end up with 0 minus 1 over 2 minus s, and then we end up with the function 1 over s minus 2. In the same way that we did this problem, we can show that in general, the Laplace transform of e to the, let's say, at, if we change this 2 by an a, we end up with 1 over s minus a. And we have our second property for the Laplace transform. Okay, I think by now this is enough. Let's stop here, and then in the other video I will continue computing more Laplace transform and telling you more about properties of the Laplace transform.